Yeah, hello, right. Yeah, thank you. First of all, I would like to thank organizers for the invitation. And yeah, today we'll speak about our work with Volodya and Kostya. And it is about principal Chiral model, which I probably should not really introduce and advertise in this audience, because it is a systematic example of two-dimensional integrable quantum field theory. So I just ultra briefly summarize the main points about it. So the classical action has this form where the field G lives on the plane or cylinder and takes values in SUN group. Obviously, on the classical level, it has SUN left times SUN right symmetry, which is realized by left-right multiplications. But the symmetry also survives on the quantum level and organized particles. Namely, each particle lives in B fundamental representation, and there are n-1 of those with the following spectrum. The integrability on level of S matrix means Young-Baxter equation, which once combined with other things like unitarity, crossing, minimal analyticity, fix S matrix uniquely. And end-to-end particle scattering is factorized into the product of 2-in-2 scattering. The last thing which I want to introduce is chemical potentials. They enter the action through the long derivatives along time direction, explicitly as written here. And now I want to put the stereo on the circle of circumference L with some particular state which contains a certain number of different particles. And the very leading effect of finiteness of L will come from the periodic boundary condition, or in other words, Bethe-Ansatz equation, which I symbolically wrote here. And it has a form of the balance between the phase which particle alpha acquires going along the circle and phases coming from the scattering with all other particles in that circle. So in what follows, I will work in thermodynamic limit, which implies that L goes to infinity and number of particles goes to infinity in such a way that the ratio or concentration is finite. So in this limit, we can write the continuous version of Bethe-Ansatz equation just by taking derivative of the log of this original equation. And the vacuum energy will be given by this, in the presence of chemical potentials, will be given by this formula. So it means that we should scan over all possible states, calculate energy, subtract this contribution from chemical potentials, and find the minimum. So practically, it is useful to go from densities to pseudo-energies and rewrite this equation in this form, in form of spectral equations. So as you can see, it is a system of n-1 coupled integral equations for pseudo-energies which have a finite support. And once it is solved, the vacuum energy is given by this simple formula. So now let's make a choice, a particular choice for chemical potentials. Namely, let's choose it along the first discrete Fourier multi-linking diagram, which actually reminds the profile of masses, as you can see, yes. And in this case, turns out that all supports of all epsilons are the same, and this system of n-1 equations after discrete Fourier transform can be collapsed to only one integral equation, which is explicitly written here. And the vacuum energy is given by this formula. The question which I want to ask now, it is expansion of vacuum energy at large n. So the very leading order was calculated in '94 in paper of Volodya, Fatiev, and Wigman. So, and it has form of semicircle with radius, which is defined by this transcendental equation, where k1 is Bessel function. So to get this solution, it is actually quite straightforward. So one needs just to keep the very leading term in 1/n expansion of the kernel, plug in this equation, and yeah, a semicircle will appear. So in the same way, one could expect to get higher corrections in 1/n, just to make a formal 1/n expansion, but actually it will not work. And to understand why, let's take a look into numerics. So this yellow semicircle, it is just a leading order semicircle, and blue line is exact numerical solution. As we will see in the bulk area, semicircle is quite good approximation. However, something is going on around the boundary, and the scale of this boundary area is 1/n. So if theta is of order 1/n, it means that omega is of order n, and the ratio of omega over n is of order 1. It means that we cannot formally make 1/n expansion here, at least if we are near the boundary. But in the bulk, it is okay. In the bulk, we have theta and omega of order 1, and we can proceed with formal expansion in 1/n of this kernel. So, and it is actually our strategy. So we split it in two parts, in two areas: bulk area, where we perform that formal expansion for the kernel and write some formal solution, and the boundary area. So where we use Wiener-Hopf method to write asymptotics near the boundary. So namely, we take exact solution, subtract bulk asymptotic, and get something localized around the boundaries. And then we sit around one boundary and think about it as a semi-line. So skipping all details, just let me show how the sketch of the algorithm. So in the bulk, we have this formal expansion, and then the closed system of equation comes from the match of asymptotics near the boundary and near the bulk, which can be written, roughly speaking, in this way. Where this epsilon, it is Fourier of this guy, this R bullet, it is just formal 1/n expansion for this kernel, and G plus and G minus, it is so-called Wiener-Hopf factorization for the kernel, and plus minus means that this function is analytic in upper and lower half plane. So then it can be in any given order in 1/n, it can be truncated in self-consistent way, and we can calculate energy in quite algorithmic way in any 1/n order. For example, in first three orders, the answer is here. And yeah, so all these i's and k's with indexes, it is Bessel functions with argument beta 0. And it is expansion in 1/n, and once again, it is exact in coupling. So now we can check it in different regimes. So let's start with weak coupling. So weak coupling corresponds to the regime when H much larger than M, or in other words, B much larger than 1. So then formal expansion of the formula from the previous slides gives us energy as a sum of two groups of terms. So the first one perfectly match two-loop calculation, direct two-loop calculation, and also actually it reproduces what we will get. We applied a kind of small modification of our method to calculate weak coupling expansion at finite n. So actually our method also works for finite n and weak coupling. So in two loops it will give this answer which match this direct calculation, and it matches this one. And also there is second group of terms which are exponentially smaller, and they correspond to Reiner-Malone. So yeah, Reiner-Malone can be thought physically as certain graphs and divergences of certain graphs, and also from the asymptotic non-Borel reasonability of this asymptotic perturbation series. So namely, there will be a pole in Borel plane, and it will produce this stock phenomena with imaginary part. Yeah, as I already mentioned, we can also apply the same method for weak coupling. But what is interesting to mention here, but it is not yet finished. So there are actually higher exponential corrections of this form. So you see the difference here. You have extra factor of n, yeah, and it can be actually matched by a so-called key-Newton classical solution of principal Chiral model, which Uhlenbeck found 30 years ago. Actually, all solutions of Euclidean equations of motions for PCM is classified as key-Newton solutions. Yeah, and also it was shown that the classical action of all the solutions are quantized, and the step in this quantization perfectly match this step here. So it means that actually the whole weak coupling answer is quite complicated. It has this form. So yeah, we have actually this identification of coupling constants through B, which comes from the weak coupling, and weak coupling is really so. And yeah, we can write it in this way. And you see it contains asymptotic series which responds to perturbation theory, and then different types of exponential corrections. And in front of each exponential correction, you will have again asymptotic perturbation series. So, and it should be resummed in some right way to get a number. Yeah, so usually people name it as resurgence program to write the whole trans series and resum it. Okay, so it's one of these directions, but today I want to actually make focus on another one, namely on strong coupling, which corresponds to the regime when H goes to M, or equivalently B goes to 0. So in this case, expansion for the energy, so once again, I just take this formula and take limit of small b. So it has this form. And there are several interesting observations. So the first one is already on the level of very first term. So if it were just a finite n principal Chiral model, in strong coupling regime, we would get delta power 3/2, what means 3 fermions. And typically, yes, if you have particle theory of particles, you will have some power dependence. However, here we see a non-analytic logarithmic dependence, which is typical for string theories. For example, absolutely the similar thing appears in SQL1 matrix model, which is dual to 2D string. And the fact that we here deal rather with extended objects than individual particles is actually already visible from the very beginning. So here the profile of masses, if you fix the mass of the most massive one with index integer part of n/2, so and send n to infinity, you will get a continuous profile of masses, yes? And also we have a magnetic field which goes along the same profile as masses, and H goes to M. So we excite all this continuum of particles simultaneously on the same footing. So it's, yeah, it's about such type of collective excitation. Okay, so the next observation will come if you now erase logs and check the powers of n and delta. You will see that they are coupled and come in a synchronized way. The similar thing happens for B. And actually, if you rewrite energy through the B, you will get a perfect match of B and N and no any logs or whatever. And that's, of course, calling for double scaling limit and resummation. So double scaling limit reads as n goes to infinity, b to 0, such that their product is fixed. And turns out that this resummation, to make this resummation, we don't really need to make resummation. We can take this limit directly on the level of original integral equation, just after some rescaling and keeping leading terms. we get this very simple integral equation for a regime of double scaling. So kernel is here, and only one parameter is B or delta, which are related, yes? So, and the energy in this case is given by this formula. So the relation to original parameters, I should say, is a bit tricky. So for example, if you have standard 't-Hooft limit, you send G squared to 0 and to infinity such that their product is constant, yes? So here it's a bit more tricky. So imagine that you want to reproduce double scaling for a given small b. So you should solve this equation for this small b, calculate this energy, get epsilon, then you can calculate right-hand side, then you have this number also, and now you send n to infinity and delta to 0 such that this equality holds. So it's, yeah, it's a bit indirect, but quite explicit. Okay, good. So on this level, we can check also some regimes. The simple regime corresponds to small b goes to 0, and it's just reproduce ordinary strong coupling fermions in original model. But in the case when small b goes to infinity, we actually surprisingly get expansion which looks as a V coupling expansion. So for some potential integrable models with B tilde support, yes. And yeah, and here is example how in this particular limit, this small b is related to original parameter. So here I decoded this implicit relation. So and now you see it has very clear form of certain expansion, yes. Okay, so at that point, people who are familiar with matrix model will recognize the similarity of the line of my talk to Siegel-1 matrix model, which are dual to the D string theory. And it is precisely the moment when we should make a conjecture and interpret this vacuum energy as partition function for the dual 3D non-critical string theory, with string coupling constant is 1 over B tilde. So let me, before we start to discuss it, let me ultra briefly summarize the story about Siegel-1 matrix model. So yeah, it is a very long story with hundreds of papers and authors. So I apologize that I didn't put names and papers here. But I copy pasted nice pictures from Igor Klebanov's lectures. So, and it goes in this way. Everything starts with one-dimensional string theory, or in other words, with a resummation of all possible embeddings of two-dimensional surface in 1D. And doing it with triangulations and going to dual graphs, one can recognize the one-to-one correspondence to Feynman graphs of this matrix model. So then when the size of this dimension goes to infinity, only the vacuum contribute. And this expansion, yes, has looks as partition function for strings with coupling constant 1 over n. On level of vacuum state, the matrix models actually reduces to free fermions in cubic potential. And this cubic comes from this cubic. Yeah, and interesting that that there is a regime when Fermi C almost overflows this hill, and combining this near threshold regime with large n, one will get such type of expansion for the vacuum energy. Okay, for second derivative, which is suspendability, but it doesn't matter. So, and as you can see, it very reminds us our expansion here, yes? So it looks very similar, just even on level of formulas. Yeah, and then indeed there is a double scaling limit. So you should multiply this mu critical minus mu Fermi by n, and it gives the proper double scaling limit. And in this double scaling limit, this double scaling limit is dual to these SQL1 strings. First thing to stress, it is emergence of one more dimension here, yes? So in a picture of matrix model, one more dimension actually comes just eigenvalue of this big matrix. On level of, in continuous language of string theory, it comes as Liouville mode. Also, probably I should comment on the role of this double scaling, its role at least twofold it. On one hand side, it provides us with a proper regularization for very dense and very big triangulations. And at the same time, it's actually washed out details of polygonalization. Yes, I said triangulation, but in principle, you can add here higher vertices. It will mean that you have not only triangulations, but general polygonalization. And of course, the continuous limit of discretization of surface should not depend on this polygonalization. And if you are in this double scaling limit, so you are in vicinity of this maximum and it does not feel what's going on far left and far right. Okay, good. Now, yeah, very good, thanks. Okay, now let me summarize in one table these two stories. So on one hand side, we have 0+1 matrix quantum mechanics. And in case of principal current model, we have 1+1 matrix quantum field theory. On level of vacuum energy, in matrix model, everything reduces to free Schrödinger equation for free fermions. And in our case, vacuum state reduces to integral equations for fermions. Then in both cases, we have similar type of Lagrangian expansion. And in both cases, combining this Lagrangian expansion with near threshold regime, we have a double scaling limit. And actually, this double scaling limit even technically looks similar. In both cases, it governs by VKB asymptotic. So here it is literally VKB asymptotic of fermions on the top of fermion C. And in our case, under the VKB asymptotic, I mean this expansion. So this expansion in the bulk looks as VKB asymptotic for particle in oscillator potential, yeah? And in matrix model, it is inverse oscillator potential. Yes, so and here in matrix model, we have 2D SQL1. And here we make conjecture about some 3D string theory. So the first question to ask, of course, what is the nature of third dimension? And it is actually quite clear. So it is certainly come from Dynkin diagram. So we already have time, we already have space, and also we have a label of Dynkin diagram. So to make it more visible, let me go a few slides earlier. So here, as you can see, I choose the first Fourier mode along Dynkin diagram, yes? And this system of n-1 equation reduced to 1. But in principle, we have n-1 pseudo energies, and in Lagrangian limit, this index should be promoted to continuous, and it will play the role of third coordinate. So for example, what we try to do, we try to take more general chemical potentials. No, for example, we can take a second discrete Fourier mode, third, etc., calculate energy and interpret it as dispersion relation for propagation along the Dynkin diagram. Well, actually, if I pronounce already words about propagation along the Dynkin diagram, let me show one more formula from one auxiliary slide. So it is a discrete Fourier modes, which I mentioned. It is just eigenvectors of Cartan matrix, and that's all. So, and the kernel in Fourier space has this form. And as you can see, omega and pi, which is index along the Dynkin diagram, enters in quite similar way. Yeah? So you can think about pi as momentum along the Dynkin diagram, and it has a form of propagator along the Dynkin diagram. Okay, so yeah. Yeah, that's the main statement, that's the main conjecture. And there is a lot of questions to understand. So first of all, as I already mentioned, there are exponential corrections, and it will be good to write it in terms of trans series and sum. And actually, it is not it's not only about the coupling. Probably in double scaling, they also survive. Well, I did not finish calculation. I don't have these coefficients for the moment, but it's quite clear that in double scaling, this exponents will survive. At least power is exactly double scaling parameter, you see? And b, it is exactly small b, and it is exactly 1 over G string. So it turns exactly in non-perturbative string correction. Yeah, the question, so what about this coefficient? We will survive in double scaling limit or not, but at least power certainly survives. Okay, another thing about on level of quantum field theory, one can ask about form factors and correlation functions in this double scaling limit. So actually, S matrix dramatically simplifies, and probably it will be possible to calculate this object. For example, in large n limit, this gentleman's calculated form factors and correlation functions. So yeah, also maybe if it will be simple enough, maybe it will be a good playground to test SUN separated of variables representation and rewrites to them. Fyodor will talk us about SU and SUV later. Then, as I said, the main question, of course, to understand the nature of third dimension. And yes, as I already said, what we're trying to do right now, we try to excite higher modes, more general profile of chemical potentials. Of course, it will be very great to have some description like effective action, as Dazhevitsky did for C=1. So it will serve as a string field theory. And in our language, it actually means that we should give life not only to Winkin label as third coordinates for this guy, but also for include time. So for the moment, it depends just on Winkin label and theta, which is momentum. And there is no dependence on time. But if we were able to include dependence on time, it would be great. Okay, the next thing, will be also interesting to reformulate, to find some class of physical observables and find scheme-independent relations between them. So what do I mean? I mean the following thing. So here, as you can see, I wrote expansion and say that 1 over b tilde is string coupling. But for example, here you can see that I did shift by log of 2. So what does it mean? It means that actually there is degrees of freedom about choice of the scheme. Yes, things like coupling constant are scheme dependent objects. So, and for example, level of weak coupling, this shift with log of 2 exactly corresponds to going from one scheme to another so-called MS scheme in perturbation theory. So in strong coupling, it's also, there is such a thing. And for example, in matrix model, it was introduced the higher derivatives of energy with respect to cosmological constant, and then some simple functional relations between them were found. So probably something similar can be done here. Of course, it would be great to introduce finite temperature, or in other words, finite cylinder with twisted boundary conditions. But technically, it is a super complicated story. So despite the fact that we have exact equation at any coupling for twisted boundary conditions on cylinder, so it's absolutely unclear how to take direct large n limit for all these Wronskians, which contains few functions with some discrete shifts, etc. But maybe in our particular case, there will be some pattern which will help us to understand how to do it. For example, here we had semicircle, and semicircle is everywhere, and it's helped us to do it. Maybe there will be some structures there. So in once we will have and finite temperature, finite cylinder means compactification of target space, and then it can allow some strange things like vortexes with some wide numbers around this circle, or maybe black holes, etc. Yeah, thank you.
Thank you.
Yeah.
So we have some minutes, a couple of minutes for a question. I think Anton first.
Yeah, okay. Evgeny, could you do some, when you talk about weak coupling, when you talk about full weak coupling resummation, is there any expectation you have? You want to capture some non-perturbative contributions, or there is something more?
So all non-perturbative discrete contributions which can appear, I already described. So it is this type of Reiner-Malone type, and it is such powers which very likely should be interpreted as just semi-classically. So I don't see other power corrections.
So that's all. There shouldn't be others.
Yeah, I think yes. But the question how to resum all this stuff properly.
So another question by Pedro.
Yeah, just a naive question. Could it be that there would be something that one could see about this third dimension already at the classical limit? Can I consider the sigma model, add this magnetic field, study the classical integrability of the sigma model, and see something going on with the Lux connection and the spectral curve? Or
well, you mean something you want really in 3D, or so on level?
Already at the classical limit, there is some sign in the density of states or something that I could see that would be a signal of this third dimension that you are mentioning.
Yeah, usually this things with spectral curve, a classical spectral curve, appears when you take the limit of. So it is different. It is different limit when you send theta to infinity. You expand S matrix, just keep the leading term, and it efficiently gives you spectral curve. So it is certainly different limit, because here it's very important what's going on the boundary, and this expansion which I just described corresponds in our language to just to the bulk. So in this way, no, I think. But if you want something in 3D, quasi-classical in 3D, well, I don't know. So what can it be? So how again you want to think about it? It's some large charges along all dots of Dynkin. So it is quasi-classical in all charges.
I thought that this magnetic field, that you knew how to add it to the action in some simple way, right? You just, I forgot, but you know better.
Well,
right?
it's just
times some trace of G-1 dg, right?
Yeah, just this one.
Right. So you have this magnetic field.
Mm-hmm.
Is this resulting model still classically integrable in the usual way? And does it have some special features when this magnetic field is small, which would be the expansion close to threshold? Or
Can we maybe stop now and continue in the discussion section, which is, I mean, we have plenty of time there. What do you think?
Okay, I can later comment about classical limit of this model with chemical potentials or with twisted boundary condition. Actually, it is known stuff. So there are, people know how classical solution will look like for any general, I think, twisted boundary condition or chemical potentials. So in classical limit here. Yeah.
Okay, nice. So I'll wait for the discussion. Very good. Thanks.
Okay, yeah. I also have some